So that is done on a 3-bus example in our text, where in this example system, we will choose bus 1 as a slack bus, and commonly we choose the magnitude to be 1 per unit and the phase angle to be 0. Why choose anything else? Okay, it makes sense to keep it at 0. And bus 2 is a PV bus where voltage magnitude is specified as 1.05, and the power that's going in is 2 per unit. Okay, whereas bus 3 is a PQ bus, and the load on this is 5 per unit, but please note that it's specified with a minus angle, because the convention is that power is going into the bus. Since this is a load, so power is coming out, right? So that's the minus sign. And the reactive power is 1 per unit, but again with a minus sign. That is the reactive power here, as shown by the direction. It's coming out, and therefore the minus sign. So with all these, and using this procedure that I talked about, associated with Newton-Raphson, here is the solution. Okay, and this is in the form of a MATLAB program, which is on the CD connected with this textbook, so one can run it and get the voltage magnitudes and angles and all these 3 buses, and then compute all the power flows on the lines as well as through the generator here. Okay, so that's shown here. So this can be verified very easily by going to a commercial program, and in our laboratory we use this wonderful program called Power World. It's a very graphical tool, and it's ideal for educational purposes, I would say. And moreover, the student version, which also comes with the textbook on a CD, it's free. It can be downloaded from the website of Power World. Probably you may want to get the latest version. So I'll recommend, if you want to use this program, go to the website of Power World and download it. And you see that very graphically it shows what is going on in this 3-bus case. And this is in actual megawatts and megawatts. But if you convert these in per unit, and knowing that 100 MVA is the base, you'll see that these numbers that you have are exactly what are shown in this diagram on this slide over here. Right? All right. So having done all that, Newton-Raphson, then it brings us to what is called a fast decoupled Newton-Raphson method. Okay, so the observation here is that that power is not very sensitive to voltage, only to the phase angle. Okay, and therefore this term could be crossed out. Similarly, the reactive power is not very sensitive to bus voltage magnitudes, and therefore this term can be crossed out. I'm sorry, I did something wrong here. Delta Q, no, I'm sorry. It is all link. All right, starting again here. Power is, differential of power is not very sensitive to voltage, so this term could be set to 0, okay, approximately speaking. And similarly, the reactive power is not very sensitive to bus voltage phase angle. So this term can be set to 0 here. Okay, so if we do that, then this matrix equation that we have on the top reduces to 2 simpler set of equations. This one and this one over here. So these can be solved much more rapidly than the full Newton-Raphson. Okay, so if you want to have a very quick answer, which is somewhat accurate, well, you can use this here. Okay. So this is done quite commonly. So that's an option. And then this equation here also shows the sensitivity of reactive power to voltage. Okay, So here we can do the sensitivity analysis where the change in reactive power is given by the change in voltage by this equation, and therefore the change in voltage can be obtained by inverting this matrix and written in this form here. So by changing the reactive power at any given bus, we can see what the change in voltage would be on that bus or other buses like this. So it's a very good tool for deciding where to locate, for example, the static VAR compensation, in which bus it would make most sense. Okay, so this Newton-Raphson method also leads to this sensitivity analysis. And the other thing is that when we go to solve power flow on any system, limit may be reached on, for example, reactive power on one or more buses. Okay, and if that happens, then it may be a PV bus. So PV bus turns into a PQ bus. So in a PV bus, only the real power is specified, right? But reactive power is not specified. But if this reactive power hits a limit, or its limit, then this PV bus turns into a PQ bus, because you want to keep that reactive power at its limit. Okay, so that's what's being shown by this 3-bus example over here, that if you hit this Q limit on bus 2, then this PV bus right here turns into PQ bus right here. Okay, and when that happens, we have you can say that Q is also specified in terms of this limit right here. So we end up with another equation, and that is shown in this bold characters right here, this 4th equation right here. So 3 by 3 certainly becomes a 4 by 4 set of equations here, as shown. Okay. So with this, I think we are ready to summarize that we have shown the need for power flow. We have shown how to represent the system for carrying out this power flow calculations. What are the basic equations? We wrote those. And in detail, we talked about Newton-Raphson procedure. And we saw how it can lead to fast decoupled Newton-Raphson, and also how it can allow us to do sensitivity analysis, and what happens when at one or more buses a VAR limit is reached. Okay, so thank you very much.